Okay folks, so today we are going to discuss landmarks. It turns out to be landmarks lecture is a landmark between where we are and where we need to go, so we had to get to it. We kept postponing it, but it's inevitable. Plus it seems not to also have a 3D necessary ordering before MDPs. So we need to complete this. Okay. I don't plan to go into all the details of this. I'm assuming that since it got, since you read a paper and since probably I also gave you the access to this a while back, you probably know what's going on, and if you have any specific questions, I'm hoping that you will bring them up. Otherwise, I will try to quickly go through an overview of their use, the way they defined and their use, and then move on to the Markov decision processes, which is the next topic. Before I get there, some administrative things. I gave all of you, those of you who put your papers up there, I marked one of your 3 papers as the main one to read. I will basically give a time frame for that to write a report on that, and also depending on the time you might present it in the class. So that's one of the paper reading by yourself. That would be different from any surveys, any reviews that you would be doing during the class. So this is not the only paper that you'll be reading. Like for example, you read the landmarks paper and wrote reviews on that. I also requested that you put up your project proposals by October 6th. I gave some ideas, but they don't have to be used at all. You can use your own ones. If you have no other ideas and you're trying, one of the things I listed there sounds interesting to you and you want details, you can come and talk to me. But eventually, you will still have to do the project. You have to, you have to flesh it out and you have to do the project. Okay, and then finally, regarding the class survey, based on that, I'm going to actually wind up giving a homework for each major topic. So, for example, I will give a homework for the planning one, as once I go back, and then similarly there will be one for MDP and so on. We will also be doing the sanity ones, which somehow will be combined with the homework. And since it's a graduate class, I will let people do the world's best project and not do anything else and still pass this course. As far as I'm concerned, that's the only thing that matters really. Okay. But on the other hand, if your project isn't going anywhere, then these things will essentially be used to decide, what your grade is. And there would be a midterm. I don't know about the final. That was another question that people asked. There will be a midterm because actually I'll be off one day in October, at least 1 or 2 days in October to LA, and that would be a good time to have a midterm. Okay. Any questions? Okay. So as I said, it's up to you. If you have a great project lined up and you don't want to write any of the homeworks, that's up to you. Okay. So don't complain later on that somehow my originality was inhibited by you, asking me to do project, homeworks. Some people want the homeworks, so I'm giving that, and then that's the way it is going to be. Any questions? Okay. I'm not really sure how deeply to go into this. Essentially, landmark-based heuristics have become reasonably popular of late. People have used landmarks. I think back in 2001, they talked about how to compute landmarks. The idea of island-driven search has been known long before. So, for example, if you know what your goal state is and you know that certain islands have to be passed through to get to the goal state, then you would essentially get to be able to find paths from the start state to the first island, then from there to the second island, so island hopping all the way to the goal state. And if it is a state space view, then essentially concatenating the paths will get you from the initial state all the way to the goal state. I think what's interesting in the landmark based heuristics direction has been that people try to look at automatic ways of identifying landmarks. And as you probably realized, identifying every landmark is going to be p-space complete. Okay, but there may be some landmarks that you might be able to identify efficiently, and then you will try to use them. Okay. I think in the beginning when they came up, when Hoffman, Porteous and Sebastian, this is actually 2004, but their original paper came in 2001, when they looked at some ideas, in particular, if you remember, how many of you looked at these slides? Okay. Well, I'm basically going to pick some of them and then you just have to go and look at the rest, because I've been mentioning earlier that I don't do a partial summary of this. Okay, so the idea of landmarks discovery that was used in Hoffman and Co. was essentially to start by saying that every goal is a landmark. Obviously, if you have to achieve a goal, if the goal state is a conjunctive goal G1, G2, G3, then you need G1, G2, G3 to be done. Okay, and what's more interesting, in fact, before the landmark work was done, there was some work by Hoffman and Co. In the IPP planner, where they talked about goal orderings. So if you have a conjunctive set of goals, G1 to Gn, then clearly they're all landmarks, because if you need to ultimately achieve all of them to reach the goal state. The question is, in what order should they be achieved? If you happen to know the order in which they can be achieved, then remember the discussion I had regarding the strips stuff, right? So if you know the serialization ordering, then you can just work on each goal separately, get a plan for each of those goals, and then just concatenate them. And that's a dream for lots of reasons. And so in fact, the work on landmarks originally was used in the context of this IPP planner. They did these goal orderings heuristics, and they used this in the context of IPP planner, which is sort of a graph plan implementation. And then he sort of separated it out of that discussion and then basically said, well, you can essentially do this not just for the top level goals, but also for propositions that have to be true on the way to the top level goals. Okay, so the idea of goal orderings, so landmarks have orderings. So landmarks are more general than goals, and landmarks have orderings. And if you know how to figure out landmark orderings, in some sense you're also figuring out how to what the goal orderings are, what the top level goal orderings are. And if you happen to know the top level goal orderings, then you have a serialization ordering of the goals. So then presumably you can work on the goals in that order, one after other, and concatenate the plans. Okay, so now the work that essentially has happened is they came up with some obvious ideas. One of the things is the top level goals are landmarks, and if B is a landmark and all actions that achieve B share A as the precondition, then A is a landmark. Not surprising enough. Okay. What is interesting is this analysis actually will find some landmarks, but may also not find some of the landmarks. So for example, what happens, all actions that achieve B either have A or C as landmarks, and then all actions that achieve A or those that achieve C have D as a precondition. In which case you sort of disjoin and then again you become important. So even if you are interested in single landmarks, single landmark propositions, you can have essentially, B is a landmark, and all the actions that achieve B either require A or require C. And then all the actions that give A and those that give C all require D. And so D becomes a landmark. Okay, so if you just did conjunctive propagation, then you will miss D being a landmark. If you also keep track of disjuncts, then you will find D as a landmark. Now the question, of course, in keeping track of disjuncts is, it can become out of hand quite quickly, right? So you would start with 2 disjunct, then that might become an 8 disjunct, then it become a 10 disjunct, and theoretically it is possible that this entire 10 disjunct will require a single conjunct as a precondition of all the actions that support any of these 10 conditions will require C as the precondition, in which case C becomes a landmark after having gone through disjunctions. Okay, but it's also likely that you wasted all your time and that disjunction never collapses. Okay, and that's why essentially you saw in both these slides as well as in the brief summary of these slides in the paper that you read, she points out that Sylvia Reister, she points out that they put a limit to the disjunction. So you don't allow the beam to go out of bounds. Okay, so the beam is always allowed to be between K and 1, right? And so that's one way they heuristically reduce the amount of work they do. Notice that they are not giving any guarantees about finding all landmarks. They're finding some landmarks this way. Okay, so there is this way of finding landmarks, and of course when you're doing this, as I said, you can either keep the conjunctions or you can also keep disjunctions up to size K. Okay. The other thing, so this is basically the disjuncture landmark part. The other thing that Reister was talking about is actually, it's kind of interesting that some ideas get tried once, especially those with sort of an empirical flavor. They may get tried once, and at that particular point of time, you could show that that idea didn't, that particular heuristic is improving performance, and so you give up. And then after many years later, somebody else will try the same idea, and for a slightly different set of reasons, it works this time. And then you start thinking of credit blame assignment. Is it me, my smartness? Is it because I used a slightly different font in writing about the idea? And in this particular case, when we read the Reister et al. 2008 paper, they made it sound as if they actually, I think it's a reasonably honestly written paper. Okay. But they did say that these are the 5 differences that we have from the previous one. In fact, 2 differences. One is this domain transition based, DTG based landmarks, which is again just another way of capturing landmarks with respect to a single variable. Okay, and we'll talk about that in a minute. And the other is the way they use the landmarks, which we'll get to in a minute. Landmarks can be used either to essentially serialize the problem, so that you'll pick piece of solution at a time and concatenate them. Okay, or you can basically the way they did, which is actually use this as part of a heuristic, a path dependent heuristic. So you sort of change the notion of the old set difference heuristic which you had, where current state, the goal state, which of the goals are not present in the current state? Count all of them. This was an idea we had before. Okay, now you not only count the goals, but also the landmarks that are missing. Okay, and that way the heuristic can become more informed. Okay, and as to whether or not you just count the number of landmarks missing, or do you provide non-uniform weights to each of the landmarks, that's cost-based versus non-cost-based approach. Okay, in the case of cost-based idea, for each landmark you essentially can compute its cost in the planning graph. Okay, and then use that. Okay, now we'll get to that in a minute, but again in a minute. But in terms of the DTGs, it's not particularly. I don't necessarily believe that those were the most important that was the most important distinction between their landmark generation and the old worker landmarks. But all they were saying is, and this is actually, we might as well talk about this, mostly because we didn't talk about SAS representation. SAS representation is essentially the CSP representation, the multi-valued variable representation, as against the Boolean valued state representation, Boolean valued state variable representation. And the idea is that even if you are given Boolean representation of state variables, which is what most PDL's descriptions do, they would compute essentially the mutex clicks, okay, and then from that identify what are the multi-valued state variables. And remember, I think last class I was pointing out that if A can be 1, 2, or 3, it's a multi-valued state variable 1, 2, or 3. When you convert it to SAT, you normally tend to say A is 1, A is 2, A is 3. Okay, now what you miss, if you just do this and stop, then what you miss is A can only be one of 1, 2, and 3. It cannot be more than one of them. Okay, and if you do not capture that, if you do not realize that, in essence, especially remember, most of the planning graph heuristics were done by relaxing the negative interactions. Because you relax the negative interactions, okay, so in essence you will start likely thinking you can make both A being equal to 1 and A being equal to 2 true directly. Okay, so what's interesting, of course, is if you actually try to do a planning graph analysis after with this representation, you would then realize that A can only be 1 or 2 or 3. It cannot be more than one value. Okay, so in some sense, you could either start with Boolean variables and do full mutex analysis on the planning graphs, or you can start with Boolean variables, first convert it into some sort of a multi-valued representation, and then do relaxed planning graph analysis. And the effect is approximately the same. So in some sense, doing this SAS representation allows you to take some of the negative interactions into account, although you are only doing relaxed planning graph with only positive interactions. Okay, that's something that happens. That's an important point to understand. And so in this particular case, I guess it's a logistics domain. There is an object here. It can be in any of these cities connected by roads, and then it can also, and it can go from place to place using a truck, and then it can also get onto the plane and go to this faraway city E. Okay, and so if you were to, one of the interesting things is if it's a Boolean variable, it can only be either true or false. In this particular case, you have one variable called the position of the object. The position of the object is a multi-valued state variable. The object can only be in one place at any given time. And what are the places? It can be in A, B, C, D, truck, plane, E. Those are the places where the object can be. Okay, so that's what this is saying. So this is the domain transition graph for the object, value of the position of the object. Can be either B or truck or A or C or D or plane or E. Okay, and the domain transition graph is essentially telling you if the object is in B, what are the immediate transition it can make. Did you understand what I'm saying? So it cannot, if it's in B, it can't directly go to E. All it can do, given the domain operators, is if it is in B, it can get into truck. And once it gets into truck, then it can go to either A or D or C, because there are roads for A or D or C. Okay, and if it is in C, then it can get into plane. And if it is in plane, then it can get to E. Okay, so that's basically what this is. This sort of tells you that not only do you have a multi-valued state variable, but that state variable essentially transitions from one value to another value according to this transition graph. Yes, sir.
Is there a reason that arcs between nodes are not labeled by the action which will cause
Yeah, there is, because it turns out that what is important, I mean, actually in fact next slide she does show what the action is. But the point is there can be more than one action that might allow that arc. Okay, so in essence you are saying B is reachable from T. Okay, immediately reachable from T, and T is immediately reachable from A, and vice versa. Okay, and then each of these, the fact that this exists means there are some actions which allow that to happen. At least one action which allows that to happen. Right? Now, as long as we're talking about this SAS representation, since we didn't talk about it before, you can actually say that in this particular kind of a domain, right, you have the, if you have essentially, let's say the multi-valued state variables called truck's position and the plane's position and the object's position. Those are the only things that are interesting because you only have one object. If you have two objects, then you have two objects' positions. Okay, each will correspond to a different DTG. So one interesting thing would be that, if I, for example, in this problem, if I only have truck's position, object's position, and the plane's position, those are the three variables that are of interest. Every goal state would basically have to ask you for certain valuation for one of these variables, one or more of these variables. Suppose I said, I want in my goal state the object to be at E and the plane to be at D. Okay, then one interesting thing, one sort of a appeal of looking at these domain transition graphs is it looks as if, so I have actually one domain transition graph for the object position, and there is also a domain transition graph for the plane's position. Right? So basically, plane apparently can only be in C and E. That's it. Plane is only allowed to be in C and E because there is an airport at C, and it can be at C and it can be at E. Okay? So actually, apart from this domain transition graph, I have one more domain transition graph for position of plane, which goes C, E. That's it. So in trying to actually answer this question of get me the object to be at E and the plane to be at C, it looks as if for the object I only have to do the search on this, and for the plane I only have to do the search on this. Do you understand what I'm saying? So there is a way in which you can split the search such that you can work on each variable independently. Of course that's not true, right? Because this is one of the reasons for one of the answers for the question that was being asked previously. When I am, for example, making this transition C to P to E, right? The plane's position is also changing from C to E. Okay, so one way of thinking about it is the planning becomes easy or hard based on the level of coupling between these multi-valued state variables and their domain transition graphs. Okay, if there is no coupling, that means while you are changing the value of this variable, object variable, the plane's position doesn't change. Let's say. Then you can actually look at the plane position part of the goal separately from the object position part of the goal. So they are like two independent goals. You can work on a plan for both of them separately and just concatenate them in each way. Okay, and to the extent planning becomes harder, it is because the DTGs have interactions. Okay, there's an entire body of literature. In fact, between the FF planner that you looked at, and that we mentioned, I think, because that's the one that used the planning graph heuristics. And then the current day Llama planner, which used landmark heuristics. There was another planner, of course there are many more, but called Fast Downward. And what Fast Downward did is to think of planning as essentially a coordinated traversal of the domain transition graphs corresponding to the different variables. Okay, and then they try to essentially see, if I have 10 variables, I'll try to see which of them are independent, which of them are dependent. So for example, I have, each variable has a domain transition graph, and I can also have, and this is actually a digression, okay, I can also have, in this particular case, changing the value of V0 affects the value of P. Right? So I have one more graph called causal graph. One more graph called causal graph. And this is basically what Fast Downward did. Okay? In the causal graph, the vertices, so in the domain transition graph, a domain transition graph is separate for each variable. The vertex in a domain transition graph is the value of that variable. Each vertex corresponds to a different value of that variable. In the causal graph, the values don't enter at all. All you care about is the variables themselves. Okay? So here is multi-valued variable 1, here is multi-valued variable 2, here is multi-valued variable 3, here is multi-valued variable 4. In this problem, this would be, let's say, the object's position, okay? And this will be the plane's position. Okay? Okay. Suppose, by the way, it turns out that, just to make it interesting, suppose in this domain I also have actions which will change the color of the plane. Different colors can be, the plane can be painted into different colors. Okay? So then the color would be a separate state variable, and it has different values. Red, green, yellow, violet, whatever. Okay? And that could be like, for example, plane's color. Okay, now the interesting thing is, I would put an edge between two variables if, in trying to change the value of this variable from one value to another, you will indirectly wind up affecting the values of this variable. That means they're coupled. And if there are edges, then basically what happens, if there are edges, then what basically happens is, any connected subset, you should think of it almost as if it is a single super variable. And try to do the planning for the valuations of the super variable. If there is no connection between these guys and these guys, then these can be done separately, these can be done separately, and the plans can be combined. When you do the super variables, what happens essentially is the super variable itself has a domain transition graph. And its valuations are in the Cartesian product of the valuations of the individual variables. Okay, in the worst case, if you are stuck with a really bad planning domain, everything affects everything. And so the domain transition graph really cannot be decomposed, cannot really be decomposed. Okay, and anyway, so what Fast Downward did is, it looks at the structure of this causal graph, looks for sort of, connected subgraphs of it, and uses that information to actually drive the planning. Okay, and the amount of independence in this graph, that means if there are disjoint components, then you can essentially get to work on one subset separately from the other subset. And there's a little more than that in fast downward. In fact, they also consider orderings between. So in fact, you could wind up having these edges can sometimes have directions. And then you could actually say that, let's say suppose there is a direction like this, then I can say I will work on these two and then extend that plan to account for this variable's value. Whereas this variable is completely independent. I could do anything with it. Okay, independent means there is no order in which to work on those variables. If they are dependent, in some sense there is an ordering between which variable should be worked on first and which variable to be worked on next. Okay, so that's sort of the background in why DTGs are interesting. But in this work, actually, all they use DTGs for. So actually, there are two main concepts to understand about DTGs. One is the SAS representation. One is the DTGs, which is the domain transition graphs, and the other is the causal graph, which is where the vertices correspond to the variables themselves. Okay. In Reister's paper, she actually only focuses on the DTGs, not the causal graph at all. Okay, and in fact, the fast downward planner was famous and was popular because it was the main aspect of it that caught people's imagination is this causal graph, and there is this idea called causal graph based heuristic, which we just completely skipped over. Okay, you can read that. I'll give you links to the paper. What Reister used essentially is just the DTGs part, and she was saying if I am given a DTG, I can compute landmarks not on the whole problem but just for this variable. So in particular, if I look at this, I realize that if V0 is originally at B and then eventually the object eventually has to go to E, then clearly it has to pass through this and this. Right? That's what DTG is showing you. Now it's possible that while it is passing through this and this, certain other variables are in turn forced to pass through certain values. That is something Reister doesn't compute. Okay, so again she's just computing a subset of the landmarks. Her landmarks correspond to individual variables' values. Okay, so that's basically every path from D0 to D passes through D dash, then D dash will be a landmark. Now what does D dash being a landmark mean? That means that this variable must be equal to D dash. That is the proposition you are considering as a landmark. That's her idea. Okay, again it will only compute some of the landmarks. In particular, it does not see that while doing this, maybe you will induce a certain pattern in some other domain transition graph. Okay, in which case if you find that, you will get more effective landmark information. Okay, the other thing, the last thing actually, which seems to be a more general idea, and I mentioned this too earlier, and in fact they have done some work, Reister and some other people have done some work on this, using this idea, and I again gave a link to a paper to you guys. All that does is, it's sort of a simpler idea which connects it to planning graph. Okay, you start with the planning graph, assume that the start node, whatever is the planning graph, you can always put a dummy start node. Suppose there is the initial proposition layer, you can put always a dummy start action, which just gave all the initial propositions. Okay, let's assume that that is that. Okay, then that basically in the planning graph, let's say it gave 1, 2, and 3 in the first layer. Then you will realize that 1, 2, and 3 will have A as their label. That means to be able to get there, you need to have started. Okay, and then 1 gives B. This is as I'm going forward, I am computing the planning graph, and I'm also propagating some labels that I can eventually use to get the landmarks out. Okay, so in this case I took 1 to B, 2 to C, 3 to D, and so that basically means D will have A and D, because everybody has their own landmark too. Okay, and this is A and C, this is A and B, and here I got one more level. This will still have AB, this has ACD, and this has AD. Okay, and I continue like this, and then if I stop here, then essentially for each of the final layer propositions, I know what actions are required to be taken. Okay, in this particular case, the labels that are being sent are the action labels. This action gives 1, 2, 3. Okay, and from this action I do action B, and from this proposition I do B. Okay, and so it gets this guy's label plus its own label forward. Okay, so the labels essentially tell you what are the action landmarks that you have to pass through. Okay, and so in some sense this is a cleaner approach, and it turns out that it gives a set of landmarks which they say are causal landmarks, in the sense there is a causal reason as to why you must go through this landmark to go through the goal state. And they differentiate causal landmarks from incidental landmarks, where just because of the initial state you will wind up going through a certain proposition value. So if it's actually raining the whole day, then if I'm going from this building to that building, becoming wet is part of the process. But becoming wet doesn't actually get me anywhere. It's just today it's raining and so I will become wet. Tomorrow it won't be raining, so I won't become wet. Okay? But whatever it is, passing through that that particular fountain area is a landmark, assuming there is no other rest of the world and I cannot actually go around, then I have to pass through the fountain. Whether it's raining or not raining, I will have to pass through the fountain. Okay, so that would be called a causal landmark. Okay. And one of the other things is they also talk about how you can use orderings between the landmarks. I didn't spend that much time on that, but those are important too. In this particular case, if A is in the ordering for, is in the label for F, then A is sort of ordered to come before F. Okay, so you can get these kinds of orderings too. And what else? So the other part, so there are like basically heuristic methods for computing landmarks, and you might say this all looks ad hoc because why don't you give me all the landmarks? Because finding all the landmarks is actually harder than finding the solution to the planning problem. Okay, it's like finding all the landmarks is like finding perfect heuristic, essentially, which would be solving more than just the current planning problem. Okay, so in terms of using them, the original idea used it as sub-goals. That means work on one of the landmarks from the initial state to the first landmark. Suppose you have a bunch of landmarks and they have partial ordering, then you get a topological sort on the landmarks. Okay, initial state to the first set of landmarks in the topological sort, and from there to the next level, and from there to the next level. Okay, so in essence what then happens is when you get from initial state to the first level of landmarks, you actually will get a real complete state. And that will become the new initial state, and this next island becomes the goal state. Okay, which is not too surprising. That's the way you would use islands, landmarks. So you go from here to the first landmark, from there to the next landmark, from there to the next landmark. And then you concatenated all these plans. And that's one way of solving. Okay, they tried that. That's the one originally it was tried. It wasn't competitive with respect to planning graph heuristics at that time. It's not a bad idea. There are worse ideas than this, but it just wasn't competitive. Okay, the other thing that they tried, the Reister paper tried, which you guys read, is an interesting idea where, so let's look at sub-goals. This is the, work on each sub-goal, and then when you get the new complete state, then from there get to the next sub-goal. Okay, and then in fact this example points out that sometimes this would be that will give you a reasonable plan. So for example, here they have a set of landmarks and the partial ordering between them. So then they'll need to first go from initial state to these, and from whatever state you get to this, and from whatever state you get to this, and so on. Okay, and if you do that, in fact in the bottom they are writing the plan that you would be doing for piece by piece by piece, and it turns out that for this problem, in fact, that plan turns out to be a pretty reasonable plan. Okay, so you go from, you put drive truck, first of all, wherever the truck was, drive it to B, and then put the object in, then drive the truck to C, then put it into the plane, then fly the plane to E, then put the object up. That's what this is saying. So in some sense, this is your skeleton of what the plan eventually looks like. And it's better than it's a skeleton in the sense that exact actions that you need to do are not being constrained. All you are saying is, when you start, you do this, get to this point, then get to this point, and then get to this point. Which specific actions you use to get from one point to another is left to you. Okay? And then they also show another example for Sussman anomaly, where the landmarks that they computed look like this, and if you just follow the same subgoaling idea, then they get a pretty ugly, long plan. Okay, it's a non-minimal plan. It will solve the problem, but it's non-minimal. And then so we talked about the fact last class that if you have a non-minimal plan, minimizing it is quite costly, can be quite costly. But definitely there won't be any optimality. Okay, so that's the point that they make on that. Yes, it can lead to much longer plans. In terms of heuristic estimates, again, interesting thing of course is this is a part where you should kind of make sense of this. Just as relaxed plan heuristics became popular in planning community because FF, which used relaxed plan heuristics, won the competition, but it also used 8 other techniques, and it was not very clear which specific combination was the most important thing. Okay, and similarly, landmark heuristics have become popular in the community, and if you read, let's say, the latest IPC, ICAPS or AAI proceedings, there will be a bunch of papers on landmark heuristics. And they became popular because Llama actually used them to win. But as I mentioned last time, when I was discussing Llama, like 2-3 classes back, Llama not only uses landmark heuristics, it also uses FF heuristic. And in fact, it uses 2 different cues. One for FF heuristic, one for landmark heuristic. And the jury is out as to whether what is important is to have 2 different cues. It doesn't matter what the 2 different cues are, or whether in fact one of them has to be landmark heuristics. I mean, to give credit to the authors, they themselves actually in the long paper, they themselves bring that up. That, while we use it, it's not very clear whether that is the reason we want. Okay, so that's kind of a nice point, but it's an interesting, if you were to use landmarks as heuristics, it turns out that they are a different type of heuristics. They are not the normal kind of heuristics because in essence, they are path dependent heuristics. So the idea is, if you are at a particular state, what you would like to say, remember that if you don't have landmarks, you can compare this state to the goal state and take the set difference between the goal state minus this. So any part of the goal state that is not in this state will count as cost of heuristic. Okay, now what I would like to do is generalize that and say a state is if a state is considered good if it has already achieved all the landmarks. Now the interesting thing about landmarks is you just pass them by. You don't necessarily hold them. So for example, I tell you that, in fact, those of you from India know that we tend to give, at least when I was a kid, when we would write a postal address, we would actually give landmarks to the postman. We won't just say 509, Temple Drive, Tempe. That's just kind of, that requires Google Maps to be present. Okay. Instead, what we will say is get onto your truck, and then you will be passing by this particular gas station with a red sign. After you pass it, then you will see a dog on the right hand side. I mean, and then you make a screeching U-turn, and then the first house is our house. This is what we used to do. Now the interesting thing is these are all landmarks. I mean, the idea landmarks comes because of the way we give directions to people. These days, that whole part of our life went out the window. We just give the address, and then even if we don't give the address, they can stalk us and come, because Google Maps shows your picture as well as your home's picture. But nowadays, if you just give the address, that's enough. Okay, but in the old days, you would give actual landmarks they have to pass through. But when they pass through the landmarks, they don't actually pick the landmark and hold it to come to your home. Do you see, by the time they come to my home, they don't have the gas station in their pocket. They don't have the mad dog in their pocket either. They just pass them by. To see whether or not you are in the right direction, the way you figure out is whether the path you have followed, like for example, after a while, I still haven't seen Rav's, house. Am I in the right direction? No, but I did pass the mad dog, so I must be in the right direction. Okay, so you count the number of landmarks you passed by. Okay, so that's why you need to know the path to the state. This is a big deal because in A-star search, you don't care about how you got to the state. You only care about what's the cost. I mean, in trying to figure out how far the state is to the goal state, you don't care about how you got to that state. Do you understand this? To figure out the G value, you need to know how you got to the state. To figure out the H value, you don't need to know how you got to the state. You only need to know how to go from this to the final state. But when you have landmarks, then the way in which you came to this state somehow seems to matter, as to whether it's a state in the right direction or not. Okay, and so that's why they call it pseudo heuristics, and it is a big difference from the A-star search point of view. It changes what it means for the for it to be a heuristic. And so then what they do is the rest of the paper is about how do you keep track of the path, and you say that a state which you took a particular path P to get to that state, it has accepted the following landmarks. That means it passed through these landmarks. Okay, so the cost of a state with the number of landmarks satisfied by the state given a path pi to that state is the total number of landmarks. The number of landmarks that still need to be satisfied by a state S to which you got to using path pi is the total number of landmarks of that state, of the problem, okay, minus the ones that have already been accepted in the path to S, okay, plus sometimes some landmarks have to be recomputed. Okay, so for example, you will see a gas station. You see lots and lots of gas stations. As soon as you leave this, there is a gas station. And you can say you will see a Chevron gas station. Well, I see a Chevron gas station both on rural road away from my home and rural road closer to my home. Which Chevron gas station are you talking about? Okay, so in particular, since we are talking about just the valuation, the truth-falsity valuation of propositions, you need to consider the fact that certain landmarks may have to be added again. And that's basically what they count as the required again landmarks. And the way they compute the required again landmarks, a landmark is required again by path pi in state S if A is already false and it's a goal. So remember that I ask you to come to my home for a party, and I ask you to bring some coriander leaves. I don't know, I feel like coriander leaves, which is also called cilantro, by the way, on the way. Okay, and so cilantro is a landmark. In the sense, if you don't have cilantro, you haven't solved the problem. And unlike the mad dog, which you don't have to be holding by your hand when you come into my home, if you don't have cilantro, I would send you back. Okay, certain landmarks actually have to be held because they're part of the goal. Okay, so that's what this is saying, false goal. The second is that I will say that then stop by. So for example, this, whenever I go to Sauvaro Lake. How many of you have been to Sauvaro Lake? So yeah, I don't know what you guys do, but there is a beautiful place called Sauvaro Lake right out there. And if you go there and you want to park, and they say you must already have the some sort of a Tonto National Park car pass, which very conveniently is sold only at stores in Tempe. Right? Right? They don't sell it there. Okay, so you should already have had that before you got there. So in essence, what happens is certain landmarks might be required because they are preconditioned to certain other landmarks, which are then on the way to the goal. So I don't need the cilantro for myself, but I told you, you see the gas station, you give the guy in the gas station some cilantro, then he'll tell you how to get to my home, right? Then of course you need the cilantro to be holding up to the point where you pass the gas station. Okay, and that's what is the second part, open prerequisite. And those are the ones that you basically are heuristically recomputing which landmarks which were already passed by. I passed by, picked up cilantro, so I'm done. No, but you're not done because you have to be holding cilantro until you come to my home or until you pass through the gas station. And those are what are being added. This is how you boost up the heuristic value. Okay. So if you compute this as the landmark heuristic, this is the landmark heuristic. The other issue is the cost-based landmarks. So here you are just counting each landmark, that's not present as adding 1 unit cost. But you could also say some landmarks require more actions than other landmarks. Okay, and so to do that, actually, in fact, in the main Llama paper, I don't remember whether the 6-page one has it, main Llama paper, they point out that they actually use cost-based heuristic because they use cost-based plans. I mean, they have to provide cheap plans in the end, not just fewest number of actions, but so actions can have costs, and also some landmarks might be harder to achieve. So the fact that it's missing counts more against you than some other landmark which only requires 1 unit. Okay, so for example, in the blocks world, hand empty is going to be a landmark half the time. Because after you're done, you put all the blocks, then your hand will be empty. And hand empty is also the kind of landmark which may be true now, but it will become false again, it will become true again, it will become false again. And it's also the kind of landmark that you can achieve. If you feel as if your entire world depends on your hand being empty, you throw whatever you have in your hand down. One step, and you got that landmark. Whereas another landmark, just to get that landmark you may need to do like 5-6 steps. So that's the cost of landmarks issue. Okay, and to compute the cost of landmarks, what can I do? For each of these landmarks, I can have my relaxed planning graph sitting next to me, compute the relaxed plan length for supporting just that condition. And if the actions have non-uniform cost, then I need to do this on cost-sensitive relaxed planning graph. Okay, which I did not specifically talk about, but it's not really that hard an idea. So for example, suppose I have P, Q and R, and then P and Q can support A1, and to do A1, I'll charge you 5 units. Okay, Q and R can support A2, and to do A2, I support 7 units. Okay, and then also P and R will support A3, and to do A3, I need 10 units. Okay, and then let's say A3 gives J, and A1 gives M, A2 gives W. Those are the effects. So the question then is, these are all zero costs. That's why these actions basically, they were true in the initial state, so they didn't cost you a thing. Okay, now when you did these actions, this is the cost of each of these actions. That was part of the problem description. Now what are the costs of M, J and W? So in fact, I may also say that and A2 also gives M. So what's the cost of M?
Because I need the cost, so that next time when I do another action here, and if it requires M, what is its, how much, I mean, the action itself has a cost, plus there is a cost for achieving its preconditions. Do you follow what I'm saying? Okay, so in this case, this is 5 units costly, this is 7 units costly. M can be achieved either by this or this, so what is the cost of M? Come on guys. 5, okay, so minimum. Okay, and similarly, A3 gives 10. A3 is the only thing that gives J, so J's cost is 10. And A2 is the only thing that gives W, W's cost is 7. Okay, now here is an action which takes J and M and gives, let's say, P. No, not P. Not P. In fact, it can give P, that's a different story. But it gives, say, Z. Now, this action's cost itself is 3 units. What's the cost of Z? So I have M 5 units, J 10 units, the action is 3 units. What's the cost of Z? What? 18. If you do 18, then you are making a specific assumption, which is similar to a similar assumption you made previously. You know, if I just tell you the following thing, here is P, I mean, you know, here is a precondition. So here, like, here is M, which requires 5 units. M, which requires 5 units. J, which requires 10 units. An action which requires 3 units just to be able to do that, and these things will give you Z. What is the cost estimate of Z? Okay, I can say it is, you know that some function of 10 and 5 plus 3 is the cost of Z. The question is, what should that function be? Simple idea says add up. Okay, if you add up, then you are assuming that these two preconditions are independent, essentially. That means the cost you incurred in trying to make M true is completely independent of the cost you incurred in making J true. You can do max, f of 10 and 5 is max of 10 and 5. If you do that, then you are assuming positive interactions. That means the cost of achieving M and J is is at least the cost of achieving the cheapest of them. I'm sorry, the costliest of them. Costliest of them. Okay. So you have a sum. So one is called a sum propagation. The other is called a max propagation. Which cost metrics do you think would be admissible? Which cost estimates would be admissible? Max ones. Which would be more informed? The sum ones. Okay. In general, when Llama winds up doing cost-based landmark evaluation, then for each landmark it needs to compute its estimate, cost estimate. So it again it's basically doing this cost propagation over the planning graph. Okay, and you have to decide whether you're doing sum or max. If you want admissible, then you do max. If you want more informed, you use sum. Yes. If you want to make it more, so if you do max, you will certainly get admissibility, but you lose informedness pretty badly. Okay. What you would really like to do is do something like sum. Except sum essentially assumes independence, and so it might be double counting some actions. So most of the action, pardon my use of the word action, but most of the action in this area of cost-based admissible heuristics is to take the sum and distribute the costs appropriately, so that you would get an estimate which is A guaranteed to be a lower bound, and B, hopefully better than max heuristic. If it's a lower bound and better than max heuristic, it's a more informed heuristic. That's what the point is. Okay, one other interesting thing about caste-based propagation, by the way, is the first time so previously you would look at, if you are looking at level-based planning graphs, you normally look at the first level where this proposition that you're looking for appears, and then they take the index and say that is the estimate of cost of this. This will not work if you're doing caste-based propagation. Why? Because there is always a really costly option which is always available. It's just that that option costs $10 million to execute. Okay, and so for example, like now of course apparently Boeing is going to allow space travel. So if I need to go to my home in India, and my old home in India, I could basically, if I have enough money, then I can say space travel. By next instant I'll be at my home. But then there are cheaper ways of going to my home, cheaper, which will take more time. Okay, I mean, even if you don't like about space, if you just talk about normal travel, right? I mean, there are, if you don't mind getting your, sleeping bag and sleeping in the airports, you get cheaper tickets. Whereas if you don't want to have any layovers, you get costlier tickets. What now, the level at which the lowest estimate for that particular condition comes in is the time that you expect when you will be able to achieve that. The time is different from cost. So many a time, M might come in the first level, a particular condition might come in the first level with 10,000 units cost. And as you go forward, its cost keeps reducing. Remember, hitchhiking is the cheapest way to go to LA, right? But it would take indefinite amount of time to get there. Planes faster, okay, cars somewhat faster, not as fast as planes, but cheaper than, costlier than hitchhiking. So the one question then becomes, if you have a cost-based planning graph, when do you stop propagating? When do you stop growing the planning graph? Do you understand what I'm saying? I mean, this is an issue. I mean, it's not that it's impossible to solve, but there is this worry that if you just keep adding more and more actions, you might find other ways of, certain actions will come in after their preconditions come in and they have cheaper cost overall. It's not enough just for the action to come in, because the action might be able to come in. So for example, my overall goal is to kind of read something, look at a painting that's in my home, my old home in India. That's my overall goal. A sub-goal of that is to be present at my home. Okay, if I achieve the sub-goal of being at home by space travel, then the cost of taking a look at that painting is the cost of space travel plus cost of looking up. Okay, or I can also say, cheap planes, and 8 days later I'll reach home and then I look at the painting. That will be a cheaper cost but longer time. Okay, this is something actually, I should have mentioned, many things can be propagated on the planning graph, including labels and including costs. And one thing that we might come back to at later time is if you're doing temporal planning, where actually actions have durations, then this trade-off that I mentioned to you becomes an important issue. What are you trying to optimize? Are you trying to optimize the cost? Are you trying to optimize the make span? Are you trying to optimize some random combination of both? Okay, again, so I kind of made a detour here and said basically this whole cost-based planning graph thing, there are slides on it in the very end of the last class's slides. I just didn't get through them. But the bigger point is, if you have that information, then you can actually use the real cost values for the landmarks and see how much cost you have to incur. Okay? there is this whole idea of admissible heuristic estimates. I'm going to skip over it. That's actually, in fact, that corresponds to some of the issues you're talking about, which is how to distribute the cost across the preconditions. You know, even if that's not the right way to do it, you are ensuring that by doing that, you are, you know, making sure that you don't cross admissibility threshold. Okay. So there is, in fact, currently using landmark-based heuristics for admissible planning is sort of a, you know, interesting area for people who are interested in optimal planning. And for them, you know, there was a paper by, I think, Karpas. In fact, this part is, you know, all the other slides were by Sylvia, and then from here is Karpas' work, because he actually did some work on this in terms of how to split the cost so that you don't double count. Because the worry about admissibility is you double count. A particular action gives both P and Q, and you count action A's cost both in P and in Q. Okay? Instead, what these guys do is do half and half, for example. That's the lowest thing, but you can do better than that. Okay? Unfortunately, with all that information, actually, the optimal planning with this heuristic is better than optimal planning with relaxed plan heuristic. But optimal planning as a whole is much less scalable than satisficing planning. Not surprising. Okay? That's all that. There is this other thing which, again, you know, since we probably seem to have gone through the class, I should probably mention this too, that landmarks are sort of implicit goals. And actually, this is an interesting way to get into the next part, which we will start today, and then we'll really do it next class. The point is, we acted as if all that matters is getting to the real goal state, which is one final state where certain things are true. Landmarks are actually not about the final state. Some of them are, you are passing through certain propositions, certain states where some properties hold. Okay? So you could actually say that instead of just saying, come to my home, I can tell you, come to my home by going onto the rural road, passing by this particular, gas station, and looking at the mad dog, and then making a U-turn. Then come to my home. Now this looks like a much harder goal than the original goal. And if you can have other ways of coming to my home, you might be wondering, why you give me this kind of micromanaging decisions? Okay, this is obviously a goal which is actually not just a goal of attainment. When you come to my home, I'll ask. In fact, people who give you directions normally tend to ask, so did you actually pass by this gas station I told you about? And if you say, no, I took a different path, they look all heartbroken, because they very carefully typed the landmarks and you didn't follow them. Okay, so landmarks, we actually use them as speeding the search. But I could easily also say that you should come to my home, but you should go through these states before coming to my home. So I could have goals which are actually trajectory goals, which tell you not just what needs to be true in the end, but certain propositions should be true. After some point of time after that, certain other proposition should be true. Some point of time after that, certain other proposition should be true. And finally, the goal proposition should be true. The old goal proposition should be true. This could be my goal itself. And if you have those kinds of goals, then actually you need a representation language for representing those goals. And from a logical point of view, you would need like temporal logics. Okay? And what they are saying is, you could, if you have landmarks, sometimes there are people who have shown how to convert those kinds of landmarks into linear temporal logic formulas. And there are planners which can essentially handle linear temporal logic formulas and essentially cut out paths which fail those temporal logic formulas. And that thereby, you could think of this either as you're making my life harder than it needs to be, just tell me where I need to be. Or you can think of this as I'm giving you information so that you won't stray from the right path and get to my home very fast. Either way, so you can think of these LTL formulas as control rules which are trying to put you to the right goal state, or you can think of them as real goals. It's not just enough to come to my home. You have to pass through Safeway and get the coriander leaves and then come to my home. Then I will say the trajectory goal is this. Okay, and so that's what they were saying, that you can convert landmarks into temporal logic formulas and then do more general reward models. Okay, and then use that. Okay, so I will stop here and mostly just to get you into a different frame of mind before you come to the next class. I wanted to show you this slide about Markov decision processes, which actually brings up what I just mentioned, about these generalized reward models. Now, when we are doing these MDPs, fall down one level in the expressiveness. In all planning, we essentially said deterministic worlds and goals of attainment is what we have been looking at till now. Goals of attainment is you need to reach a final state where certain properties hold. That's it. That's what all planning problems have been till now. When I gave you landmarks, normally they were only to just get you to that goal state faster. Really, I couldn't care less whether you've passed by this gas station or not. My assumption is that most plans will probably pass through that. So if you have realized that, you can reduce your search effort. Do you have a question? Okay. So deterministic worlds and goals of attainment, for which the atomic model for doing the problem is graph search. Is graph search, right? Basically finding paths between nodes in a graph. States are essentially vertices, actions are edges between the states, and you're finding a path from one state to another state. And doing it in propositional level is what we have been doing in the last 7 classes. Last 7.5 classes actually. Okay, now, what if I have a different kind of a problem where I have stochastic words and generalized rewards? A generalized reward is whenever you pass through a state, you get a reward. And when you pass through a sequence of states, you get a reward that, in the simplest case, a summation of the rewards that you collected in all these states. And so that's generalized reward. Now, this is more general than the goal of attainment. Landmarks kind of are like generalized rewards. You're saying, I don't just want you to be in the final state, I want you to go through certain states where you get to collect some little rewards there too. Okay, and then the other interesting issue is when you do an action from a state, you don't necessarily go to a single state, you might go to a set of states with some probability distribution. Okay, so what I would be doing is going from here to here, which sort of generalizes in 2 different directions. So in some sense, whatever we will be doing in terms of MDPs is a more general problem than this. Okay, so I could have deterministic worlds and generalized rewards, which would be like, for example, trajectory goals are like that. Okay, I can have stochastic worlds and goals of attainment. That means it doesn't really matter what you go through, it matters whether you reached a final state. I can have both together. For reasons that sort of are historical, we look at both of them together. Okay, and the question is, if I have both of them together, what is even the atomic model for search? At least in the previous case, A star is the atomic model for search. The solution is a path, and A star is the model for finding that path. The question is, if I have a more propositional and relational representation, how do I exploit that? That's what we spent time for the last several classes. Now we go, when we made the problem more general, it turns out we realize, unless you have done MDPs before, at least this model doesn't work anymore. What is even a solution in that case? And as an example of a problem like this, think of a robot which is in this grid. Okay, and it starts from here, its start state is here. Okay, and these 2 states are interesting in the sense, if you get here, after this you cannot go anywhere. It's a sync state. And then you get +1 as the reward. and you get here, you don't go anywhere, and you get -1 as the reward. So each state has an immediate reward, and if that state is also a sync state, then the immediate reward is the only reward you will ever going to get after that, because you don't get to go to any other states. Okay. Beyond that, I will also say that every other state, while you get through that state, basically that state gives you an immediate reward, which is -0.04. Think of that as move on, move on, move on. Get to your main goals. Don't waste your time in me. Okay, I could change this reward function anyway, but if suppose it's -0.04, then the interesting question is, what is the solution for this problem? Presumably the objective for the agent would be to maximize the rewards they collect. Since every one of these small states are dinging them with -0.04, they want to run fast and get to this. That would be a good way of getting, maximal reward. Now, obviously, if this was not a sync state, then they can keep coming to this state, and every iteration they'll get +1. But it's a sync state. They will only get +1 once and they stop. Now the question is, what should the agent be doing? Normally, if it's a deterministic domain, then it's like finding the shortest path from start to +1. That's what it is. Okay? If it is a stochastic domain, and such that if I try to go in one direction, I have some small probability of going in the two directions perpendicular to that. This is a very simple example where if I want to go up, I will go up with 0.8 probability, go right with 0.1 probability, and left with 0.1 probability. Now, you'll see what do you mean by going left from here. If you hit the wall, you stay in the room. If there is no other room next door, then you just stay in that same room. Okay? So if I try to go up from this guy, with 0.8 probability I will come here, 0.1 probability I will come here, 0.1 probability I will come here.
If you run into a wall, will you update the probability to 0?
What?
If you hit the wall going left, will you update the probability for that square to 0?
No, so the point, this action is being given, you could do that way. In that particular case, that action would be different. The description of that action would be different for this particular state, but you could actually say there is a generalized action which you can do this from any square, and the assumption is that if you hit the wall, then it's like staying in that same thing. Okay? So now, in this case, what is the solution? The solution, it turns out, is no longer a path from going from here to here. Okay, now before I get there, give me 5 more minutes, okay, and then we'll just get back again. So, if I just have, apart from +1, -1, I also had a +2 here and a -2 here. And it's deterministic. Then what is the solution? What is the solution? And no, imagine that, and so then you have to go up here. If this is a sync node. If it's not a sync node, then there is a problem anyway, because you can get infinite reward, which is something we'll talk about later. Okay. Now, if it is stochastic and this is the problem, then in essence, what you need to do is you need to know what best action to do whenever you find yourself in a particular state. And a mapping from states to actions is what is needed, and that's called a policy. And a plan is just a partial policy. In the deterministic worlds, you know that if I can go up, like this, like this, like this, and I don't need to tell you what happens when you find yourself in these states, because you'll never find yourself in those states. If you follow my directions, you won't find yourself in those states, because it's a deterministic world. In a stochastic world, even when you are trying to follow that, you might find yourself here. Then what do you do? And when you're trying to get back here, you may still stay here. And after a while, when you try to go this side, you might come into this state. In general, when you have a stochastic domain, every state, the reachable set of states becomes much larger, even when you are following one default plan. So really what you would need is a policy which is a mapping from states to actions. Okay. For this particular problem, for those numbers, which is -0.04 as the reward for the middle states, and plus 1 here, minus 1 here, we'll figure out that the optimal policy for this problem would look like this. So when you're here, go up, when you're here, go up, when you're here, go this. Now, when you're here, go up, and when you're here, come this side. And even when you're here, don't go up, go this side. This is an interesting part, right? Because it turns out that you're being conservative. If you try to go up and then go this way, then you might go into this. If you're stuck here, you may as well try to get out this way. But if you are here, try to go like that. Okay, that turns out to be the optimal policy. We have to figure out how to compute that. Okay, but the last thing I want you to understand is just by changing these rewards, I can change what it means to have an optimal policy. Okay, suppose if the reward I said here is minus 0.04. If I were to I have some algorithm that we will talk about for computing optimal policies, the value and policy iteration. And if you use them and you change the reward such that every state gives a reward which is uniform but less than minus 1.6284. That's a magic number for this problem. If that is the case, what happens is that this is the classic case of depressed people. The life is unbearable. The life is unbearable, you want to end it. Right? So you will notice that while this guy, a happy-go-lucky guy, when he's here tries to go this way, when this guy tries to go this way. When he's here tries to go this way. The only reason it makes sense is depressed people are using a reward model. It's just the wrong reward model, that you may not like it, but they are using their own reward model. They are being rational with respect to their reward model. Okay? This one is between minus 0.42 to minus 0.08. And this corresponds to this. This is sort of slightly different. In this area, when you are here, you actually go up. Because it's still negative enough reward that there is no point in going this far out way to come back to plus 1. And this corresponds to this range because its R is less than, R is between minus 0.02 and 0. And you had minus 0.04. So that's, this is the, in this range essentially, oh no, this is actually different too. There's some problem. But in this particular range for the reward, the optimal policy looks like this. Okay, and it tries to be more careful, it tries to, because life means something. Individual states are not making it very negative. So it tries to live longer, and so it actually goes, when it's here, notice that it won't try to go this way, it tries to go this way. That's a very cute idea. Because this is sort of like when you have to walk on a thin ledge with Grand Canyon right in front of you, okay, you would do funny things just to reduce the probability of falling into the canyon, okay? And this guy is trying to avoid the probability of falling into the canyon. If he tries to go this way, there's a 0.1 probability that he would fall into the canyon. Whereas if he goes this way, there's 0.1 probability that he'll be here, 0.1 that he will be here, 0.8 that he won't do anything, which is still fine. I will live longer and then, live to see another day. And the last thing is when every state has a reward greater than 0. And this is basically, if you have a reward model like this, then all churches will close. All pastors, priests will go home. Because the entire religion depends on afterlife, right? And you are saying, I don't want to die. I'm having too much fun. And so what you will do is just like this guy tries to find the nearest exit. This guy tries to avoid the nearest exit, whether plus 1 or minus 1. I don't want heaven, I don't want hell. I'm having way too much fun right here. Because each state is more than 0. So by just going around the states and whenever I get to plus 1, I turn back. So I don't go to Sunday church. Okay? Neither do I go to the Sunday Satanic church or whatever. I'm just basically having fun watching TV. Okay? The point is, just by changing the reward model, you will wind up having optimal policies with very different behavioral characteristics, which makes complete intuitive sense for you. So the question then is, how do we compute these policies? And if you know how to compute these policies for this, then finding a path for a deterministic problem with a goal of attainment is just a special case. So much of what we will be doing in the next several classes really is this whole thing will be a huge general case of this. The one complication that I'm still